Hi everyone, and welcome to the fourth and final video going through some past exam questions on neutralisation. Although these are mostly actually buffer solutions questions in this one, just a bit of extra buffers practice. So let's get into it. Let's have a look. What have we got? We've got propanoic acid. It wants us to write the equation for the reaction of propanoic acid with sodium carbonate. So here's my propanoic acid. And sodium carbonate is Na2CO3. And if I react an acid and a carbonate, I'm going to get a salt, so I'm going to get sodium propanoate here. And I'm going to get salt and water and carbon dioxide, right? And then I just need to make sure this is balanced. I've got 2 sodiums here, so I need to times that by 2, and therefore I need to have 2 propanoic acids to start with. Okay. And then the carbon dioxide is coming from here, and the 2 hydrogens and the 1 spare oxygen is where the water comes from. So we're fine. Then we need to make sure we've read the question really carefully, because it's now asking us for an ionic equation, but it's not the ionic equation for this reaction. This is an ionic equation for a totally different reaction, propanoic acid and potassium hydroxide. So don't fall into the trap of thinking you've got to write the ionic equation for this. Okay, just read it carefully. What we've got here, we've got propanoic acid and aqueous potassium hydroxide. So this is an acid and an alkali. Okay, and so because they're both aqueous, we don't really need to work this out. Whenever you've got an acid and an alkali, you're always going to end up with the same ionic equation. It's just the ionic equation for neutralisation. So you're going to have the H plus ions from the acid reacting with the hydroxide ions from the potassium hydroxide to make water. Okay, the propanoate ions are going to cancel and the potassium ions are going to cancel. So that's all we're going to be left with. Okay, so if we're smart, we can spot this and go, hang on, acid and alkali. It's just going to be that every time. Okay. You can't do that for any other ones. You know, if you were doing the ionic equation for this, you would have to think about it because you're going to have to include the carbon dioxide and stuff. But if you've just got an acid and an alkali, then that's the reaction that you're looking for. Right, what's going on here? They're making a buffer solution from propanoic acid and propanoate ions. Okay, fine. Concentrations are both 1 mole per decimeter cubed. We get our equilibrium. We know what the Ka is. Calculate the pH of this buffer solution. Okay, and it's only 1 mark. Now, calculate the pH of a buffer solution is usually quite difficult. It's not usually a 1 mark question. So this is telling us that this must be quite easy, right? There must be something that's going to make this question easier than you'd think. Where are we going to start? We're going to start by writing out Ka, like we always do with these kind of questions. And we want the pH, right? So we want the H plus concentration. So we need to rearrange this. Remember, this is a buffer solution, so we can't do any shenanigans with H plus squared or anything like that. Going to have to just rearrange this as it is. So it's going to be Ka times this one divided by the propanoate ions. And then what have we got? We know what the Ka is. It's 1.35 times 10 to the minus 5. 1.35 times 10 to the minus 5. And then these concentrations are both 1 mole per decimeter cubed. Okay, so this is why it's a nice easy question. It's only 1 mark. Okay, we're going to times that by 1. We're going to divide it by 1. Okay, so if the H plus concentration is 1.35 times 10 to the minus 5, then the pH is going to be the negative log of that. So let's just work that out. We need to do it to 2 decimal places. Let's be careful there. So we're going to do the negative log of 1.35 times 10 to the minus 5. And it's 2 decimal places, so it's 4.87. Okay, that's quite nice. So those both being 1 is what's made that question much easier. Okay, then last bit on this page, it says a small amount of ammonia is added. Explain in terms of equilibrium how the buffer solution would respond to the added ammonia. Okay, so ammonia is a base, right? It's going to react with the alkali. Sorry, it's going to react with the acid. So we can say added ammonia reacts with the propanoic acid, so it's going to react with this. We could argue it's going to react here. You could do it that way. I'm going to go for this one, but you could say that it reacts with the H plus and then more propanoic acid dissociates. That would also be fine. I'm going to say the ammonia reacts with the propanoic acid. So the equilibrium shifts to the right. Okay, that's important because it does say in terms of equilibrium, so it's important that we actually reference the equilibrium here. Okay, and that's actually all we need to say. Okay, we're going to get 1 mark for saying how does it react, and then the second mark for saying which way does the equilibrium shift. Okay. Right, the final part of this question is the actual sort of longer, more difficult buffer solution calculation. So it now says the student's adding a certain amount of magnesium to this buffer solution, calculate the pH of the new buffer solution. So this is more like the questions that we'd be expecting, not the little 1 mark question we did a minute ago. Okay, so this is more of a challenging one for sure. Okay, so where are we going to start with this? We're going to start with Ka, as always. So we're going to write out Ka. We're just going to copy it from what I put on the previous page. This is still the same question, right? So it's just this Ka again. Okay, so I'm just going to copy that out. And then we rearranged it, didn't we? So we'll do that again. And we'll get H plus is Ka times the acid concentration divided by the concentration of the propanoate ions. So we're just doing the same bit of rearrangement that we did in the previous question, but it's not going to be as easy this time. We're not just going to substitute in 1 and 1 and be on our way. We're going to need to calculate these new concentrations, so it's going to be a bit more challenging. To do this, we're going to need to work out what's going on with this magnesium. Okay, so if we're adding magnesium to a buffer solution, we need to think about what is that magnesium actually going to react with? What's going to happen? Okay, so we need to write an equation. This magnesium is going to react with the acid. Okay, it's going to react with our propanoic acid here. Yeah, an acid and a metal is going to make a salt and it's going to make hydrogen. Okay, but we want to be a little bit careful with how we write this. Okay, it's going to make magnesium propanoate. But I'm going to write those as separate ions because when we come to do Ka, magnesium propanoate doesn't show up in the Ka expression, right? It's just propanoate ions. Okay, so I'm going to write this as saying we're going to end up making magnesium ions, okay, and propanoate ions. Okay, and you can see because magnesium's in group 2, okay, we're going to need to make 2 of those. We're going to need to have started with 2 of those. And an acid and a metal is going to make a salt and hydrogen gas. That's going to be our reaction. Okay. What we're going to do with this now is we're going to do our ICE table that we've done with equilibrium questions, and we do it with buffers as well. So we're going to look at, right, initially, how many moles do we have? What is the change? Okay, we're going to do this in a table here. And how much is there left at equilibrium? And then we're going to need to work out some concentrations as well. Okay, we're not going to be interested in the hydrogen gas, are we? So we're not going to bother with that. And we're not going to be interested in the magnesium ions because that doesn't come up in Ka at all. So we're not going to be interested in that. We're interested in these 2. And we're also interested in magnesium because that's the one we knew about to start with. So this is where we're going to start. How many moles is 6.075 grams of magnesium? Okay. So for that, we're going to need to do the mass divided by the atomic mass. So we need to go to our periodic table. Magnesium here, magnesium's atomic mass is 24.3. Okay. So we're going to put that here. And if we work that out, we're going to get 6.075 divided by 24.3. 0.25. So that's what we've got to start with for our magnesium. Okay. Right, we need to know about some of the others. What else do we know? We know we had 1 decimeter cubed of the buffer solution. Okay. And from the previous part of the question, so we need to be really careful here. We need to go back and look at this. We know that the concentrations of both of these two were 1 mole per decimeter cubed to start with. So if these were both 1 mole per decimeter cubed, and we've got 1 decimeter cubed, then we would have started with 1 mole here, and we would have started with 1 mole here as well. Okay, so we've got to be really careful there. These are usually 0 when you're starting off with buffer solutions, but not in this question. So make sure you've read back to the start of the question. So therefore, if these two react, okay, we've got an excess of the acid, so the magnesium is all going to go, and it's going to go down to 0, okay, which is what we want. We don't want that left. And so now we need to look at the ratio. It's a 1 to 2 ratio. So if we use up 0.25 moles of magnesium, we're going to use up 0.5 moles of the acid, and so we're going to be left with 0.5 moles. If we then look at the ethanoate ions, again, it's a 1 to 2 to 2 ratio. So I'm going to get plus 0.5 here because this is the product that's going to be formed. And so I'm going to end up with 1.5 moles. Okay. But I can't just put these numbers in here because these need to be concentrations, and these are moles. Okay, so we need to do moles divided by the volume. Okay, but in this case, the volume is just 1 decimeter cubed. So actually, we could just put those numbers in. It is going to be 0.5 because we've just divided by 1 decimeter cubed. Okay. So now these are the new concentrations that we can put into our Ka expression. So the H plus is going to be equal to the Ka value, which again was on the previous part of the question. So again, we do need to keep looking back here again. Here's our Ka, 1.35 times 10 to the minus 5. Okay, this is a habit that you want to get into, is if you get stuck, go back and look at the previous part of the question. So we're going to put that in, and then we're going to put these, make sure we get these in the right places. So we want the acid concentration on the top. So that is this one, 0.5. So it's going to be times 0.5 and then divided by 1.5. So let's work that out. 1.35 times 10 to the minus 5 times 0.5 divided by 1.5. And we get 4.5 times 10 to the minus 6. So therefore, the pH is going to be the negative log of 4.5 times 10 to the minus 6. Let me work this out. So we just do the log of that and then put a minus sign in front of it. So it's going to be 5.34. What are we doing? We're doing it to 2 decimal places. So we should be looking at 5.35 for our answer here. Okay. So it's quite a tricky one, that. But again, if you use this kind of table, hopefully that lays it out fairly clearly.